This call is now being recorded.
Because of having convex formulation, having convex optimization is important because you can get the numerical solution by applying existing algorithms very conveniently. So it will be more concerned about the formulation process if you work with convex program. Okay. Now I'm going to talk about a few techniques where you can derive equivalent problem. This is very important in formulating process. We say two problems are equivalent if solution of one problem is also a solution to another problem. Okay, and vice versa. So this is kind of an informal definition. Two equivalent problems are not identical problems. Like when you say two problems are identical, it basically means that when you show it in a standard form, they are identical problems. Now let's see some example. This is some of a common technique. Okay, I give you like several pairs of P1 and P2. P1 and P2 are equivalent, but they are not the same optimization problem. They are not identical. Okay, first one, let's see. If you minimize the norm of ax minus y, the two norm alone, it's going to be the same as minimizing the two norms squared. They are not identical problem because objective are not the same function. One without the square and the other one with the square. But according to this definition, the solution x that minimize, that is a solution of P1, that's going to be the same as x star that solve P2, right? Right? Because the norm function, like without a square, with or without the square, you see that the point is x star is the same. Okay. Because the square function is increasing. The example of the second pair, if you have something non-negative, guaranteed to be non-negative, maybe positive, just to avoid the zero denominator. If you maximize the reciprocal of something positive, it should be the same as minimizing the denominator. Yes or no? Right? Yes or no? One typical thing is that, I want to maximize the margin of my linear hyperplane in SVM. Okay. This thing is a margin between two hyperplanes. That's appear to be a form of 1/2 norm of W. Okay. So initially I want to maximize this, but it's going to be the same as minimizing the norm of W with or without square, same thing. The third one is that if I maximize of magnitude of fx, because I put the absolute value just to make that quantity always non-negative. All right. If I maximize that, if I put the log, it should be the same thing because the log function is increasing. All right, it's increasing. So whether you maximize the log of that thing or you maximize the argument fx, it returns the same optimal solutions. Okay, so this is a standard trick. Now we give you like several techniques. Okay, maybe I have time to do only some of them. Okay. These are typical techniques where you would derive equivalent problem. And to do it or not, all right, to do it this way or another way, it's just a matter of how you see the original problem. Okay, the first technique is that if you have linear equation as a constraint, you can get rid of some variables. This is a technique called eliminating equality constraints. And from our linear algebra review on the other day, all right, as we see many times, when linear equation plays a role of constraints, typically A should be fat. When A is fat, of course, there's a null space of A, right? The null space of A is non-zero, of course. And let's just say that you can find a basis in the null space of A, and you put those what basis vector of the null space of A in the column of matrix F. Okay, and this is how you parameterize general solution to AX equals B. We talked about it on the other day, right? And the dimension of Z will be if X is in Rn, okay, if the null space, if the dimension of null space is R, and R, how is R related with N? Bigger than N, equals to N, or less than N? Null space of A, dimension of null space of A. Less than or less than, right? Always less than, because null space is a subspace of, if A is M by N, A map from Rn to Rm, right? The null space is a subspace of Rn. The dimension must be less than N, okay? And then what? R, right? If your dimension is R, you can find R basis vector. So your big F has R columns. Your Z is in R. Your Z is in R. What's the dimension of your Z? Huh? No. Your X is FZ plus X naught, right? Your F has R columns. So your Z is in R. Huh? Rn or RR or something else. RR, right? So now you get rid of X because you characterize it in another way in terms of the variable Z instead, and that becomes a less dimensional problem because the dimension of Z is R, which is less than N. Okay. You have done it in your homework. For example, you have x1 minus 2 square plus x2 minus 3 square, and then you have what, x1 plus x2 equal 4, right? This is like the basic version of eliminating the linear constraint. Like you write x2 in terms of x1, you put it back. Now, your homework question would be something like, okay, I give you a QP. I give you a QP that looks like this, but it happens that you have only linear equality constraints. Okay. Now you will use this technique. This is your homework number 3, I think. You can use this technique that, oh, I can get rid of this. I can parameterize X in terms of Z, and then I put it back. Then you should have an unconstrained, right, problem. But when you put it back, is it still a QP or not? Now you're going to figure out, okay? When you put X as a function of Z, you put it back in the quadratic objective. Would you still get a quadratic function in Z or not? Should or should not? X is linear in Z. Your objective is quadratic in X, but the relation of X and Z are linear, right? Fine. When you put it back, what kind of function of Z would you get? Quadratic. Just work it out what it would be. Which means now you have derived what if you finish it, initially you have constraint QP, but the constraint is simple, just linear equality constraint. But you have transformed it into an equivalent problem that appears to be unconstrained. Okay? I have an example here, but I think it's easy, so I'm gonna skip. Okay. The second one is introducing a slack variable. This is a second technique where you can derive equivalent problem. You can, when you have inequality constraint, when you have inequality constraint, fi less than 0, if something is negative, okay, fi less than 0, you're gonna add it up. Okay, so it's less than 0 by this portion, by this gap. Okay, you can add this gap si, and that gap should be non-negative value. Okay, this si is called a slack variable. This is also a common technique they use in LP, in formulating LP. Okay. Epigraph form. I have explained this before, the technique, and it's in your homework and everything. It's like we have used it briefly in our previous lecture, but now let me state the principle again formally. An epigraph of a function is basically an area above the graph. Take a look. This is the curve of f naught. Okay, the definition of an epigraph is a set. Now it becomes a set of x and t. The t that you have introduced is an upper bound on your function. So it's a set of two variables. That's why an epigraph is a shaded area. This t and x is not in the epigraph of f, because if you draw with this t, your function does not lie below this t. No? Got it? No? อะไรงง this point is not in the epigraph of f, because these two, epigraph is a pair, is a set of pair x and t. Okay. At this coordinate, I call it x1 and t1. All right. It's just too thick. This is coordinate x1. This is coordinate t1. Where is my fx1? Here, right? My fx1 is here, and it's greater than t1. So it doesn't satisfy this condition. So that coordinate, that point, is not in my epigraph. This is in my epigraph because my fx1 is here, right? This is how big. This is my fx1. Okay, and my t1, where is my t1? My t1 is here. So my fx1 is less than t1. Got it? Got it? If you don't want to think too much, it's the same as saying that it's an area above the graph. This is just a math or corresponding math condition. Now, this is an example of non-convex F. Non-convex F. This is an example of convex F. Now, if you look at the epigraph, which, the name is epigraph, but it's actually a set. Which set is convex? The khaki color or the purple, the violet color? The violet color. This is a simple fact, very important fact. An epigraph of a convex function is always convex set. Now, this is the trick that we have been using a lot, okay? When you have a minimization of f naught, okay, like initially you have minimization of f naught subject to some constraints. We can transform to an epigraph form by recognizing that if you put if you introduce this t as an upper bound of f naught, okay, and then you try to minimize t, but your problem now is to minimization over x and t. That's going to lead to the same solution. Let's take a look at this, okay? Minimize t, right? Subject to f naught less than t, okay? The region where f naught less than t is actually the violet region, is an epigraph of f naught. This value of t1 is not optimal yet because there are a bunch of points here that corresponding to a smaller t and still in the epigraph. So I should lower my t, right? And then you will see that when I hit this point, I'm still in the epigraph, but my t is minimum. When you minimize over x and t, you get the t and also get the x star. This t is not feasible in this problem. Even though the violet t is still smaller than the blue t. But the coordinate, this is not feasible. My f naught x is not less than this violet t. Got it? And that is a technique you use in the homework, right? Like in our previous lecture that I say, okay, if you have one norm, right? And then we say, oh, you minimize t subject to one norm of x less than t instead. This is the same thing. Also work with non-convex formulation. Is it true? Right? This is my non-convex f. This is optimum t yet? Not yet. Optimum yet? No. Right? This is optimum yet? Yes. Okay. This is global minimum. Maybe the homework. What did you do with the homework? Homework. You minimize. Okay, this is a good exercise. Max, right? 0 AI transpose X plus BI. Now you have seen that, okay, this is sum of the max function is what? Is a max of two values, okay? Like each time, each I, the max return 1 out of 2. And you have this sum of a bunch of them. So if you allow max of between 0 and I, this is I, less than something CI. Okay. Then maybe I should write the final one. Would it be the same as I make a sum of ZI, okay, subject to the max of 0 AI transpose X plus BI less than ZI? Like forget about the sum first, right? Just for one fixed I use the epigraph form. I minimize Zi and I put Zi as an upper bound of this max. Get it? Okay? You look suspicious. No? Okay. And now I'm going to erase, all right? Because you know that the max between two values less than zi is equivalent to max of two things less than this. Those two things, both of them must be less than that thing, right? So DCI should be greater than 0 and this is n AI transpose X plus BI less than CI. And now I'm going to use a vector form. Now I'm going to like translate to vector form. How can you write it? A sum of ZI is what? Sum of ZI. 1 transpose Z subject to Z bigger than 0. And A, now I'm going to use X and Z, right? Less than A, first row, A, you're going to move Z here, right? And negative B. Is there a second portion? The second portion is Z greater than 0. 0 first and negative I 0. Okay. Now you figure out the dimension yourself. Again, this is something you can exercise, right? This doesn't look like an LP, but with this epigraph technique, okay, now you have arrived at LP.
Separate way like maximization, term to comparison, if you separate it in terms that okay, x will always be greater than equal to 0. And we say
Equal to 0?
x
X?
x is always be non-negative. Without, I mean, here we have comparison of two.
Yes.
And a plus equal to x. So it means that value of x vector will always be non-negative.
No, it doesn't mean. It doesn't mean that x has to be greater than 0. It means that after this F5 transform, whether this will be the return or out of max, this guy has to be bigger than 0. But this doesn't mean x has to be non-negative. Oh. Okay, we have exercise here, but I'm just gonna skip and okay. Maybe just one last technique. When you have a minimization of two variables, sometimes it's just two groups of variables. If you see that the constraint only contains in one group of variable, like if you look at here, it's a minimization of x1 and x2, but you only have constraint in x1, right? So it would be equivalent as if you can minimize on x2 first, because x2 doesn't have to obey anything in the constraint. So you can minimize f0 over x2 first and put it back as a new like minimized objective function. And that, do you agree that when you take a minimization of f0, which is a function of x1 and x2, if you minimize it over x2, it will be a function of x1, right? That's a technique. I have one example here. Probably we don't have time. This is an example in maximum likelihood estimation. Now you have x and d. In terms of variable x, now it's not clear how you would minimize it, right? Because of you have to know something about g. But in terms of the row in d, you see that, oh, I see the term 1 over d appears a lot. right? Log of 1 over d, and the 1 over d as a constant here. If I need to minimize it over x and d, I say, okay, I can minimize over 1 over d first. I look at this as a new variable, all right? And appear, so I take the gradient with respect to 1 over d, set it to 0, and that d is given by this expression. Okay, please verify. These appear in log likelihood estimation of nonlinear additive noise model. Okay, so the reduced problem becomes like minimizing x only, but it's the log of this guy. And from our technique we learned before, the log is monotonically increasing, right? You minimize the log of something is the same as minimize of the argument, right? Log is increasing. If x is less than y, log x is less than log y. So it's the same as minimizing the argument instead. Okay. So these are common techniques in optimization where you can derive equivalent problem. But of course, the equivalent problem that you have derived should be somehow more meaningful, should be easier to solve, right? Let me end the lecture today. Not today, just this week.